Okay, section 2.5 is a very important section. It's on simplifying radicals. So, with fractions, for example, we can write fractions in simplest terms, like 2 over 10. Your teacher, whether it's me or someone else, prefers that you not write a fraction as 2 over 10 as a final answer. We prefer you put it in simplest terms. 1 over 5, right? Well, believe it or not, radicals can also be written in simplest terms, and that's what we're going to teach you today, how to write a radical in simplest terms. First of all, though, we need to introduce you to two terms here, entire radical and mixed radical. An entire radical is a radical that has a coefficient of 1. Well, what does that mean? Well, let's take a look here. Let's say that you had a radical. Actually, let's use some letters here. Let's put M, A, and B here. And let's name these things. Okay, so I think I talked about this before. The actual sign here is called the radical sign. So that's the radical. The amount inside, whatever's inside the radical sign, is called the radicand. The little number up here, which if it's a 2, remember we don't have to write it, but if it's a 3 or 4 or 5, whatever, we have to write it, that little number up there, that's called the index. And this number out front here, if there is one, this is called the coefficient. The number up front, this would mean m times, and then the radical here. Alright, that's a bit abstract, so let's give some more real-world examples here. For example, an entire radical might look like something like the square root of 19. Okay? The radicand is 19, there's the radical sign. The index, what's the index here? The index is 2, so we don't have to write it. And the coefficient, there is none, which means it is 1. Why is it not 0? Because that would mean 0 times root 19, which is the same as 0. And no, that's not what we have here. We actually have root 19, so that must be 1 times root 19. Another example would be the cube root of 12, or the fourth root of 63, or whatever. Okay, as long as there's no number out front here, no coefficient out front, then it's an entire radical. A mixed radical, you can probably guess, it's when it has a coefficient other than 1 and also not 0, for that reason I showed you. If it's 0 out front, it actually disappears because the whole thing's equal to 0. So examples of that would be something like, instead of root 19, 3 root 19. How about 5 cube root of 2? These are examples. Alright, let's make it negative so we can show that it can be negatives too. What does this mean right here? 3 square root of 19. This means 3, I'll put means 3 times root 19. This means negative 5 times the cube root of 2. Okay, so we're going to learn two things here. We're going to learn how to go from entire to mixed radicals and how to go back from mixed radicals to entire radicals. So first thing we're going to do is we're going to learn how to change from entire radicals to mixed radicals, and what we call this is simplifying radicals. That's what I was talking about at the start of the video, right? You need to know how to simplify radicals. So this is very important. You need to put your answers, if you were to do some kind of equation and get this answer right here, root 20, we'd actually want you to change this into simplest form. So how do you put things in simplest form? Radicals. Well, there's two ways to do it. One way, you'll probably be happy to know, is that you can use the factor tree again. Gotta love those factor trees. And this is the way I find that most people like to do it. So they make their factor tree. What do you want to multiply to get 20? How about 4 and 5? 4 is not prime. That can become 2 and 2. So that's it. Everything's prime now, 2 and 2 and 5. So root 20 is exactly the same as root 2 times 2 times 5, right? Now, remember back to the club scenario I talked about. This club here is club what? What's the index out here? I don't see an index. It means it's club 2. This is club 2. So we will need to have a pair before we can take something out. I see one pair there. It's right there. That can come out front. So what we have is, well, so this 5, first of all, this 5, you can't pair it up. So what do you do with it? You leave it inside. It can't come out of the club. It has to come out in a pair, and it doesn't have its pair. It's stuck inside the club. That's okay. It's a pretty happening club. It's going to enjoy itself. So the 2's come out, and you're left with just one of the 2's. And the 5's left in. This is your answer, 2 root 5. Okay, there's another way to do it, which I'll show you. This is the way that I like to do it. It's a little bit faster. But it does rely on you more or less memorizing that list of perfect squares. So I'll write them over here, the perfect squares. I've written them a whole bunch of times, I think. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, blah, 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 keeps going. Let's just write it there. So the way you can do this a little bit faster, so I'll write again up here, root 20, we'll do the same question, is you ask yourself, what can I switch this into, this root 20, that would include one of these? First of all, never use the 1. That's not going to change anything. If you rewrote this as 20 times 1, that makes no difference. But do you see a number here that you could, is a factor of 20? First of all, it has to be smaller than 20. So right away in this question, you know that it has to be one of these three numbers. Now, there won't always be one. If there is not one, that means it's in simplest form already. But this is not in simplest form. Because do you see that 4 goes into 20? 9 doesn't go into 20, 16 doesn't go into 20, but 4 goes into 20. How many times? 5. So root 20 is the same as root 4 times 5. And here's a very important statement. Root 4 times 5 is exactly the same as root 4 times root 5. I'm actually going to write that for you in here in a second. Okay, so now what we got, instead of root 20, we have root 4 times root 5. Well, root 4 is something you know. What is the square root of 4? That's a perfect square, right? That's why it's in this list. The square root of 4 is 2. What's the square root of 5? Don't know. It's not a perfect square, so just rewrite it. 2 root 5. There you go. 2 root 5, 2 root 5. So, as I said, I want to write that for you here. So basically how I can write this for you is a times b. So any two amounts that are multiplied together and then you take the square root of them is the same amount as taking the square root of a and multiplying it by the square root of b. Okay, that's very important. And that's what I've shown you right here. Okay, square root of 300. Well, let's do it both ways again. So the square root of 300, first of all, we'll do the factor tree. 300, well, it's definitely 3 times 100. And 100 is 10 times 10. And 10 is 2 times 5, and 10 is 2 times 5. So the square root of 300 is the same as the square root of 2 times 2, right, 2 and 2, times 3 times 5 times 5. That's the prime factorization. Again, this is a club 2. There's a little invisible 2 here. We need pairs to take them out. Here's a pair. The 3 and 5 don't pair out, right? You have to have the exact same thing, but here's a pair. So both these numbers can come out. The 2 can come out and the 5 can come out. What do we do with them when they come out? Well, we multiply them, but let's do it in 2 steps. You don't always have to do it this slow, but I'll do it this slow to make sure you're clear what's happening. The 2 comes out. The 5 comes out. So you're going to multiply those two together. What's left inside? The 3. 2 times 5 is 10. The answer is 10 root 3. Okay? If you want to do it the other way, so again, I'll write root 300 here, and we'll do the same question. You decide which method you like. I call this method over here the tree method because you're using a factor tree. And I call this, I call this method over here, I call it the wall method. Why do I call it the wall method? Because chances are, unless I've become cruel and mean in my later years of teaching, up on the wall there you'll see a beautiful list of the perfect squares, so you can look up at the wall there to help you out. And yes, I won't rip them down during tests and everything. Okay, so if you're doing the wall method, you would look up at the wall and you see these numbers and you ask yourself, what's the biggest number that goes into 300? I guess I need a few more numbers up here. 121, 144, 169, 196, 225. Just trust me, none of these go into 300. The one that goes into 300, the biggest one, by the way, you want to take the biggest one. If you take the smaller one, like 4 goes into it or 25 goes into it, which is true, they do go into 300, you're going to have to, it still won't be in simplest form. So you want to take the biggest thing possible, and I see that 100 is the biggest thing possible. So root 300 is the same as root 100 times 3, which is the same as root 100 times root 3. What is the square root of 100? 10. What's the square root of 3? I don't know, so we just keep it there, 10 root 3. There you go, same answer. Same thing with cube roots. So it's exactly the same thing, except for the wall method, you're going to have a different list of numbers. But let's do the tree method first. 32. 8 and 4, if you want, or 16 and 2, whatever you want. 2 and 4, and then 2 and 2. And here's another 2 and 2. Oh, so the prime factorization is just 5 2's. 2 times 2 times 2 times 2 times 2. And this is club 3 this time. You got to have 3 before you can move out. So there's 3 right there, and you're left with 2 inside. How's that going to work? Well, let's take a look. These 2's all move out, right? So what we have is those 2's come out, and we have a 2 up front. Still cube root. Don't forget that cube root. People always forget it, and I never know what to do, whether to take marks off or not. And you're left inside with 2 times 2. Well, obviously what you're going to do then is you're going to multiply the 2 times 2 and get 4. This is the simplified form, 2 cube root of 4. If we do the wall method, so I'll write this again. You do not want to look at this list of numbers up here. Why not? Because these are perfect squares. We need to write down the perfect cubes. 1, 8, 27, 64, 125. That's probably enough. Again, don't worry about 1 because that's not going to make a difference here. Do you see one of these numbers? It has to be smaller than 32, so that leaves you with 27 and 8. Does one of those numbers go into 32? Yeah, 8 does. So cube root of 32 is the same as the cube root of 8 times 4, which is the same as, again, I'm going to write this in here for you, cube root of 8 times the cube root of 4. What's the cube root of 8? 2, right? 2 times 2 times 2 is 8, so 2. What's the cube root of 4? Don't know. The square root of 4 is 2, but the cube root of 4, you can't do that. It's not a perfect cube. So you get 2 times the cube root of 4, just like you had here. What am I writing here? Same sort of thing we did before, but this time I'm showing you it's true for cube roots as well. If you have 2 values, a times b, and you take the cube root of them, it's the same as taking the cube root of the first one and multiplying it by the cube root of the second one. These are called the product rules. Alright, next page. Now what we're going to do is we're going to find some products. So in order to do this, root 5 times root 10, look back here and you'll see that if you look on the right side first and then the left side, do you see that root a times root b equals root ab? You just have to multiply the two things in the radical sign. So in other words, if we have root 5 times root 10, guess what that equals? That equals root 50. Great. Are we done? Unfortunately not, because we need to put them in simplest form. Sometimes you will be done. Often you will be done when you multiply. But in this case, we can simplify this. So I'll just do the factor tree method this time. 50 is the same as 5 times 10, and 10 is the same as 5 times 2. Oh, so the prime factorization of root 50 is 2 times 5 times 5. We're doing square roots. It's club 2. We need a pair. There it is. That comes out front. So what we have for our final answer is 5 root 2. Next one. Whoa, this one looks confusing. We have coefficients out front. What do you do with those? Well, the rule is that you multiply the coefficients together, and you also multiply the radicands together. So if you want, you could write a little rule for yourself. A root b times c root d is the same as multiply the coefficients together. A times c is ac, and multiply the radicands together. B times d is bd. So I probably should have written that in my notes. I didn't do that. I'll add it to my notes. That's very important as well. And same thing with cube roots. If you put cube root here and cube root here, it would be same cube root here. Oh, by the way, here's something you can't do. If you had something like the square root of 4 times the cube root of 5 or something, you can't multiply these two things together because this is a cube root and this is a square root. They have to either both be square roots or both be cube roots. All right. So in this case, what we're going to do is we're going to multiply the coefficients together. 3 times negative 4. I'll actually write it 3 times negative 4. And inside the radical sign, we're going to multiply 5 times 8. 3 times negative 4 is negative 12. 5 times 8 is 40. And are we done? I don't think so, because I think we can simplify 40. 40 is the same as 8 times 5, which is 2 times 4 and 2 times 2. So what we have is negative 12 root. The prime factorization of 40 is 2 times 2 times 2 times 5. We're looking for a pair because this is club 2 square root, so there's a pair. So that comes out front. There's already a number out front, so what do? We multiply. We have negative 12 times the 2 that comes out, and what's left inside is the 2 times 5. Negative 12 times 2 is negative 24. 2 times 5 is 10. There's your answer, negative 24 root 10. By the way, you could have done this a different way. You could have simplified this root 8 at the start. Could you have simplified the root 5? No. If you do a factor tree for 5, you can't do anything. 5's prime, so there's nothing you could do. But if you did a factor tree for 8, you could simplify it because 8 is the same as 2 times 4 and 2 times 2. So in other words, what you could do is I'll rewrite the 3 root 5 times negative 4, but 8 is the same as 2 times 2 times 2. It's club 2, so we're looking for a pair. There's a pair. So what we have is 3 root 5 times negative 4 times the 2 that comes out, and what's left inside is another 2. So then we have 3 root 5 times negative 4 times 2 is negative 8 times root 2. And using this rule right here, we now multiply the coefficients. 3 times negative 8 is negative 24. And we multiply the radicands. 5 times 2 is 10. We're done. Negative 24 root 10, just like we got here. Okay, same rules apply for cube roots. So they're both cube roots. I can multiply. 4 times 2 is 8. It's still a cube root. 2 times 6 is 12. Not sure if I can simplify it. Let's see. 2 and 6 and 2 and 3. This is club 3. I don't have a 3 here. There's no group of 3. So this is it. We're done right there. Next one. Okay. We have no number out front. What number does that mean is out here? A 1. So we multiply 1 times 8 and get 8 cube root of 50 times 40. That is 2,000. Wow, should we do a factor tree for 2,000? Why not? We could do 20 times 100, and then 4 times 5, 2 times 2, 10 times 10, 2 times 5, and 2 times 5. So we end up with 8 times the cube root of 1, 2, 3, 4 2's, 1, 2, 3, 4, and 3 5's, 1, 2, 3. Okay, this is club 3, so we need 3 here and 3 here. So what we end up with is the 8 out front times the 2 that comes out times the 5 that comes out. It's still a cube root, and there's a 2 left inside. 16 times 5 is 80 times the cube root of 2. That's your answer. Again, you could have simplified. First this root 50 because 8 is a perfect cubed. And sorry, this root 40 because 8 is perfect cubed and 8 goes into that. So you could have done that first, but I'm not going to do that because this video is getting kind of long. Okay, now we're going to go the other way. We're going to change mixed radicals back into entire radicals. In other words, you want to get this 5 back into the radicand. So the way I teach this again is with this club idea. I know this is really cheesy, but people seem to get it when I teach it this way. So first of all, what club is this? There's no index here, so this is club 2. Right? There's a little 2 up there. So basically, this 5 wants to get into the club. But in order to get into the club, he needs to pick up a badge because he's just visiting the club. And his badge is sitting right up here waiting for him. So he's going to pick up that 2 when he moves into the club. So what it looks like is, here's the club. 5 is moving in, but it's picking up its visitor badge, which has a 2 on it. Now, 3 is already in the club. What we called him last year is 3 is a VIP, baby. 3 is already in there. It doesn't need a badge. It's a VIP. So that just sits like that. Okay, so what does that equal? That equals 5 times 5 is 25 times 3. You end up with root 75. And you're done. Okay, it's just that quick and easy. So, for example, this 3 wants to move into the club. Which club is it? It's hard to read, but there's a little 3 there. Right? It's club 3, cube root. So, here's the club. When he moves in and picks up his visitor's badge, there's still more visitor badge sticking out here. So don't lose the 3 here. So, 3 moves into the club. He's a visitor. He's got to pick up his badge, and the badge is a 3. 2 is already in the club. Does it need a badge? No. Why not? VIP, baby. It's already in there. So now we can finish things up. 3 cubed is 27 times 2. If you multiply that, 27 times 2, you'll get 54. The answer is cube root of 54. Okay, we're done. Important stuff. Make sure you learn this, especially the simplifying stuff. Well, learn them both, this bottom stuff as well. But the simplifying stuff you'll do a lot of from now until grade 12 and beyond. All right, have fun.